performance, but in terms of quote unquote chain of thought at 32 performance, right? So they were basically making 32 parallel calls and then had this kind of, somewhat Byzantine scheme to combine those results and pick a final answer. And people thought this was cheating. They're like, oh, you shouldn't do this. Google was like, no, this seems like a reasonable thing to do. Seems fair. And actually, they're making some good points. Like, depending on the size of the model, actually, it might have been less total compute, right? That was actually part of a much longer intellectual lineage, actually, at Google, that I actually give DeepMind some of the first credit for doing something that looks like compound systems with AlphaCode. So they released AlphaCode at the end of 2022. It didn't get much attention because this is also when ChatGPT was released. Everyone was pretty focused on that. But it was a really, really interesting method that they had undergirding AlphaCode, where they actually beat humans at coding competitions. And the way they did it was by making 1 million parallel calls to what at the time was a state-of-the-art kind of multi-hundred million parameter model. 1 million calls at once. They would ask the same question to 1 million replicas of the model. And they had this kind of interesting protocol for filtering down to the top 10 responses and then running those one by one until the test passed. It turned out this worked really, really well. It's kind of a funny scheme, but it worked. And this, this idea, this kind of concept, compound systems has broadened beyond, though, just composing ensembles to other schemes. This is one of the first instances of work on routing, which is very intuitive. Everyone does some form of this probably in production in your companies and in your work. Is this early work on Frugal GPT was looking at, okay, well, it turns out there's some notion of an intelligence level that you can saturate with a small model, right? And so you don't always need an Einstein-grade model to answer simple questions. Turns out you can just, if the question is a simple question, which turns out it's actually easier to judge the difficulty of a question than to answer the question, or easy, I'm using that term liberally. It's true in terms of number of tokens, it's true in terms of amount of compute, it's also true in terms of the intelligence required by the judge to classify. By doing that, this system was able to be 98% cheaper than GPT-4 with equivalent performance on a number of evaluations. So that's pretty exciting. And this was just based on just these two models, GPT 3.5 and GPT-4. That idea started to get a lot richer, though, and so now it's becoming clear that there is a very rich architecture landscape of these compound systems. You can actually take these inference calls and build architectures out of them, just like we build architectures out of neural networks, right? And we talk about how many parameters are in a neural network. We talk about whether these are recurrent structures or et cetera. But I think something similar is starting to emerge at this kind of networks of networks level. This is one of the early works on this. R more LM calls all you need. A very funny naming scheme. And this was looking at, okay, if you want to go beyond the kind of quality and reliability frontier accessible by today's state-of-the-art models, to what extent can you do the naive thing of just making N calls, let's say 1,000 calls, 1 million calls, to whatever the current state-of-the-art model is? To what extent can you do that and get GPT-7 performance early out of GPT-4? If you're willing to pay a higher price, right? If I told you that I'm budget insensitive, that $3 per million tokens is too cheap, my answer only requires a few tokens, I'm willing to make 1 million calls, to what extent could I do that and, in the most naive sense, actually get better performance? It turns out even this very basic scheme there's a lot of richness and nuance in the dynamics that arise here. So for example, turns out there are kind of these non-monotonic scaling curves that arise where as you increase the number of calls, you don't necessarily get better performance. Actually, performance can go down. And I'll come back to that actually if that's interesting. Performance can go down as you make more calls, but in a way that we can foresee and predict. This then spawned work on, so that was the most basic work there was on, you have some ensemble and you're just doing voting-based aggregation. So you're taking the most common response. Well, what happens if you have judge-based aggregation and some type of verifier-prover structure? What happens there? It turns out this has its own dynamics. You can characterize these systems in the same way that people often characterize kind of cryptographic systems in terms of, for example, I'm not sure if people are familiar with PCPs, but these kind of probabilistically checkable proofs, these types of structures where you characterize them in terms of the kind of proving complexity and the verification complexity. And so there's almost like a GAN-esque idea in how you can compose these systems and kind of get better performance. And so quite a bit of richness. I'll just sample a few more works and show broadly why this area is interesting, try to characterize this as an area. Here's some work on DSPy. Everyone's probably heard of DSPy from our lab. DSPy was kind of one of the first frameworks to try to systematize building LLM programs where you could actually try to backprop through and optimize the prompts right? By searching in the initial constructions, just kind of searching over potential prompts, and adding, all these kind of tricks that we've all learned, like, hey, model, I'll give you a tip if you behave or if you give a good response, like kind of iterating over those types of tricks, injecting them intelligently, or just more freely backpropping through proofs. Here's another compound systems idea, just to complete the survey. The model families concept, where now every generation of these models has a large variant, a middle-sized variant typically, and then a cheap variant that's kind of cheap and fast inference. And in this agentic context, this is more and more important. Like, you don't want to use the big slow system on kind of just parsing through websites and opening up browsers and clicking around, et cetera. That's very wasteful. You want kind of specialized models that can do that very quickly. So here's, I think, where things start to get really, really interesting, which is, I think, when these ideas started to really make their way into the kind of really common conversation in our field, is with the inference time scaling results. The initial inference time scaling results from OpenAI and the O series of models was actually kind of vertical inference time scaling, vertical kind of chain of thoughts. And so what you're doing is you're basically taking the same model, a single replica by default, and you're basically just unfurling longer and longer chains of thought. You're giving it the ability to make longer and longer chains of thought. And implicitly, at least, these models are doing some type of grid search within the token space. Kind of like vertically with one worker, so to speak. When you put it that way, it sounds like a super inefficient thing to do, actually. But that's actually what we're doing. And so if anyone's looked at the traces from like DeepSeek, you'll see that DeepSeek and all these other models, they'll often say wait, and they'll backtrack, right? And they'll be like, oh, I guess that's not the right answer, and they'll go back. They'll say, let me go back. They kind of make it so they're actually doing like a beam search or a tree search within the token space. This is very demanding, though. It requires a ton of HBM, a ton of GPU memory. And so it's challenging. It means that you need basically a state-of-the-art server to run one of these models. Or you have to do some type of model parallelism. You have to split the model across at least a couple of chips. That means it's kind of cost prohibitive to do. But people have taken these ideas, and reasoning works. And so it turns out people have been using it applied to a bunch of different agentic settings. Here's one of my favorites, the virtual lab work by James O. At Stanford, constructing these compound systems with different agents, with different personas, getting them to kind of work through tasks. So I'll skip forward a little bit. The point is there's a lot of different work going on that can broadly be called compound systems. And we've actually chronicled some of these. And if people want to add things that you like, you can add them to this repo. This awesome compound systems repo that's going to be affiliated with the conference that myself and some other Berkeley and Stanford people are going to organize. Oh, I'll go back to that. I saw some people taking photos. I'll let you do that. You can contribute to the repo. So next, I'll just give a perspective on why I think this area is so important, and then we'll talk a little bit about some frameworks for taking these ideas and actually using them to address your problems, and kind of talk to the audience about what types of problems are you working on. I'll go forward there, and we'll come back to that as well. OK, so crazy slide. You already saw it, so I'll just go into it. So first, I want to step back a little bit before I make this next set of points. And I want people to just reflect on just how ludicrous the deep learning hypothesis is, and how remarkable it is that this kind of works. Right? So if you talk to some of the early pioneers in deep learning, so I was on a team at DeepMind before starting my company Foundry. That's called the core deep learning team. And our team was actually very controversial. A lot of people weren't that enthusiastic about deep learning. It's funny to remember that, even just a few years ago. And the deep learning hypothesis was very hand-wavy. It was almost dissatisfying in some ways, but it's very intuitive and simple, which was basically, everything that we call intelligence comes from these kind of systems of neurons, that are composed of what we call the brain. The human brain is, the best existence proof for general intelligence that we know of. And so the idea was, okay, what if we can construct, it's very simple, just like if we can construct artificial systems of neurons, build them out of sand. It's kind of crazy that this works. We build these artificial systems of neurons. They're built out of silicon. They're built out of sand. We run a ton of power through them from these power plants and solar panels. And somehow, actually, turns out that does replicate, at least at the surface, does actually simulate many aspects of intelligence that we care about. At least declarative and procedural knowledge to a great extent. It's kind of wild that this works so well. Obviously, this requires, though, that these artificial systems of neurons get bigger and bigger. That we can get closer and closer to approximating the brain. It's at least the intuition that people like Ilya and Jeff Hinton and many others had going way back. And so now I'll kind of try to extend that intuition and talk about these networks of networks and give you some sense of why these things work. So stepping back and giving just a bit more context, a lot of deep learning's progression has been about bending the curve on scaling dynamics, right? We have these magical principles, of the universe that we discovered, these kind of scaling dynamics, where you build these larger and larger systems of neurons. There's a Kolmogorov explanation for these things that we can go into, but you get the idea. You have these larger and larger systems, and part of the point has been, okay, as we throw more and more flops, more and more teraflops at these systems, to what extent do we get intelligence out? Right? And a lot of research is bending the curve on that dynamic, ensuring that you get greater efficiency out of incremental flops, right? Greater intelligence out of incremental flops. And so the first era, was kind of the pre-2012, pre-GPU era. We saw compute scaling pretty dramatically for these kind of older neural network-based systems. And then since 2012, obviously, we've seen things inflect. And if people saw Bill Daly's keynote earlier, you'd know that things have inflected once again. Since the transformer era in 2017. And now things have inflected once again with these inference time scaling systems. So I'll talk a little bit about that. Here's another angle for looking at this. This is basically an efficiency curve. Let me go to the next chart so you see it a little bit better. At the same time as we've had compute scaling dramatically, as we've been putting kind of doubling the number of petaflop days or teraflop days in these systems every 3.4 months or roughly, we've also seen training efficiency go way up. So it's been inflecting up. We've roughly been getting a 2xing of the efficiency of these systems every 16 months. And so these two trends overlapping is leading to kind of the acceleration of progress. The really exciting thing is now with this inference time scaling, we're seeing the first version of this search idea is applied to the kind of intelligence gain that we get out of scaling these systems. So this is, I think, the best initial example, an anecdote, of how we've started to bend the curve on the amount of intelligence we get out of additional flops. So there's an annual poker competition, and there's a really cool story from this, which is AI poker was kind of one of the holy grail challenges. It's a kind of a hard game. It's partially observable. It has a lot of property, a lot of desiderata that you want out of a hard kind of game regime. And these systems were getting better year by year, largely by just increasing the number of parameters. So roughly what you see on that chart, it's on a log scale. As you see exponential increase in the number of parameters in these poker playing systems. This is some great work from Noam Brown. And something really interesting happened where they'd been kind of on this curve of progress, increasing number of buckets, which is roughly number of parameters. And the blue line corresponds to just standard kind of pre-training scaling. It was progressing really nicely. But then there was an observation that Noam and some of his collaborators made, which was the AI system, even in really tricky, hard scenarios in poker, it was always moving instantly, whereas the human opponent would take a long time to think. The human would pause and be like, okay, this is a challenging scenario. Let me think about this, right? And it's a common parameter in game playing systems like Stockfish to have like a thinking time parameter that you can adjust, right? Because these are search-based systems. Well, the poker playing bots didn't have that. And so Noam, in this paper that I'm showing below, they introduced search, which is another way of saying inference time scaling, on top of these poker playing systems. And you immediately saw, roughly speaking, the lower you are on this chart, the better. They immediately saw this massive shift downwards, to the point where you would have needed to 100,000x the scale if you were in this blue regime to intersect with the end point of this orange regime. And so that was just a massive inflecting, a massive bending of the curve of progress, of the amount of kind of the return to additional compute. And you see this now in a more general way in these inference time scale kind of general transformers, GPT type systems, where this was the very controversial result from I think got a lot of people's attention in the O1 announcement, just adding compute, adding additional flops on a logarithmic scale, funnily enough. So it's actually kind of a tapering off curve. And yeah, you get greater and greater pass-at accuracy. And it's funny because now this is basically what Gemini was doing back with Gemini Ultra, with the chain of thought 32. In some sense, just along a different vector. It's ironic that now this is the regime, and Gemini doesn't kind of get credit for starting to pioneer this a bit. All of this is actually part of that same bitter lesson, in some sense, right? The classic bitter lesson that search in general learning, kind of methods that can assimilate compute are really important to pursue. I think part of the intuition of deep learning, to put it a slightly different way, I noted that kind of crazy intuition about the human brain, et cetera. When I talk to some people who were kind of there at those earliest days, another thing I hear quite often is they had intuition that deep learning would work well because it was clear to them that deep learning was one of the ML theoretic regimes that would best be able to assimilate compute. That Moore's law is kind of the greatest trend ever. Compute scaling, what we've seen is the greatest exponential that civilization has ever witnessed. And so you want to kind of pursue methods that can ride that wave as much as possible. And that intuition was really, really powerful. So now you have a little bit of grounding of, okay, you want methods that can assimilate compute well. You have some notion that there's different dimensions along which you can scale compute. You can scale it vertically with deeper chains of thought. You can scale it horizontally with more replicas. There's different things you can do. There's scaling dynamics. You can kind of have systems that route among models and kind of use compute efficiently that way. You can have ensembles. So you have some intuition for that. So now we'll jump over and talk about some of the ways that you can actually start to use this intuition and bring this to bear on your problems today, but then also maybe some ideas that people can take with them if you're doing research or trying to expand the frontier. OK, so let me talk a little bit about ways to put these intuitions to work. So, and I apologize for those who were at the talks this morning. You're going to get to hear the same talk twice, parts of it. I apologize for that. And you also get to see me try to navigate. OK, perfect. Yeah, so I'll talk about, OK, so how do you actually start to bring some of these things to bear? And so it's very difficult for academics or people just in regular industry to push that kind of RL, deeper chains of thought frontier. It's very, very expensive. These systems are hard to wrangle. They're hard to understand. But people have been doing a lot of work kind of building routers, building ensembles. That's a very common pattern. Many of you are probably already doing that in your work. One just most common primitive is if you have a problem that you need a reliable answer for, people will often just call multiple models on that question, 2 times, 3 times, 4 times. And then if they all concur, if they all have the same answer, you can probably feel pretty confident that if you independently invoke them and they agree, it's probably not a hallucination. So I've met many, many companies that have some version of this pattern in production, where they have multiple models, do some type of document extraction or whatever it may be, some translation. And if the answers concur, they send that answer along down the funnel. And if the answers diverge, they invoke a BPO or bring a human in to kind of check the answer, right? Which takes a lot more time and is more costly. It makes their business model inviable if they have to do that for everything. And so what we want to do with this system Ember is we've been doing a lot of research, some of which I showed earlier, on constructing routers, on constructing ensembles of various types. And this type of research can be a little bit painful to do. There's a lot of kind of pipe building work, not the most glamorous. And so we just want to build a common research framework that all of our collaborators across a variety of companies, Microsoft Research, IBM Research, NVIDIA, Berkeley, Stanford, Google, Foundry, could use. And so that's what Ember is. And so we call it an inference time scaling architecture framework. All right. There we go. Yes, so I won't go, at this point I made earlier, but I'll just reiterate it because it's so important. We found that by combining calls to these models, you can get GPT-7 early, so to speak, if you're willing to pay the price. It might not be very cost efficient, but you can kind of get a much higher performance really, really early, arbitrarily at inference time with kind of inference time scaling. It's actually, by the way, even better if you can do this across models. These models have their own affinities. They're good at different things. Google's models are better at some things. Claude is better at some things like agentic coding. It's famous for that now, right? Some of these models have their own personality. You can combine them across providers and actually get boosts across tasks in some really powerful ways, especially in agentic settings when you decompose things. So that's improving the quality reliability frontier, but you can also improve costs. So some of the cheapest systems are 1/5,000th what some of the more expensive systems cost. And so you can make 5, 6, or more calls to some of the cheaper systems and still be 70, 80% cheaper than the quote-unquote frontier systems. So we've used these ideas and gotten really, really great results in a number of agentic tasks and published works that have recently won best papers and crossed a number of these recent conferences like NeurIPS. in some of the workshops. Yeah, so this is the framework. It's shared for research across a number of different groups. And a lot of papers actually based on these ideas will be coming out over the coming weeks and months. And you also hear about a new conference that we're starting with the ACM that you'll hopefully hear about very soon. That will be kind of a flagship conference on agentic systems and compound systems. OK, so I'll just skip through some of this since we talked about it. The only point I'll make from here is I think today when we talk about these systems, even when we're talking about these ensembles, the original Gemini example was 32 calls. It was chain of thought at 32, right? In the more extreme cases, you might make 1 million calls, 1 billion calls. And so in the future, when we talk about an 8B system, we might not be talking about the number of parameters. We might be talking about the number of calls in some inference time architecture. That's kind of a funny thing to imagine today, but I think we're not very far from that at all, particularly in these agentic contexts. And that's possible and tractable because the cost of inference is falling precipitously, and a whole host of people, from clouds like us to hardware companies like NVIDIA and Grok and AMD to companies working on distilling models, new methods for distillation, across the entire spectrum, people are working on pushing this further and further and further as like kind of a new Moore's law of our era. And yeah, there's more and more models. I think it was unclear to people a year ago whether we were going to end up in a regime with models that looks more like radio, where there's kind of 3 or 5 stations, or something more like TikTok, with kind of a vast ecosystem, a long tail of models and fine-tuned variants and distilled variants. I think the evidence is actually increasingly going in favor of this kind of much more menagerie of models kind of future, where there will be many, many distilled variants, many, many post-trained variants, many, many kind of heads, et cetera, and more providers. I think that's becoming more and more evident. OK, so I'll skip forward a little bit. Sure.
Why do you have 2 Groks highlighted with arrows?
Oh, that's actually just from the Grok. This is from artificial analysis.
I thought you had something
Oh, yeah.
about reasoning.
Yeah, I'll repeat the question. Yeah, so the question was, why are Grok models highlighted here? So this is actually from artificial analysis. And it was partially highlighting this kind of notion of a Pareto frontier, where these Grok models are, if you look here, there's kind of this notion of how intelligent is it versus how expensive is it. And Grok models are actually in some pretty attractive, at the ends of the spectrum in an attractive way. So Grok 3 mini reasoning is very, very cheap, but very, very intelligent. And so it's kind of highlighted by this independent reviewer, artificial analysis, for being really, really strong. And Grok 3 is also quite strong in intelligence and also quite cheap. Awesome. So I'll skip forward a little bit. This kind of just highlights some of the work that I talked about, how this, this observation that the cost of inference calls is falling has motivated lots of interesting work. I'll skip that point. All right. So that motivated us to create this framework Ember that I'll talk a little bit about today, give you guys some intuition about, which was just trying to make it easier to construct these types of graphs, share them. A really, really important part of why progress was so fast in the 2010s was people could build modules, build architectures, do research, and then they could share the work that they did, open source, and then people could start not from scratch if they had some new idea. You could just download, hey, someone else did this idea, just take the code, git clone it, and then I can immediately make some tweak, and get a new paper out of it. Right? That type of thing was really important. That's how you get exponential progress. Right? Things kind of stack. If everyone's starting from scratch, you don't get exponential progress. So that was Bill Dalley's point about programmability and compositionality, the point that Dalley made earlier. So it's super important in this kind of inference time scaling context. And so you need some notion of torch for this new regime. Neural network, like perceptron research, wouldn't have been very ambitious if you were doing all the neural network computations with for loops. You would never make a graph very, very large. Like you wouldn't create these GPT kind of type structures with multiple blocks, ensemble, these kind of embedding blocks, attention blocks, FFN blocks, composed with billions of parameters. You wouldn't do that if there wasn't parallel dispatch, so you weren't running things in an efficient vectorized way on GPUs. It'd be super slow. Put it simply, it'd be super duper slow if you didn't have that. It also would be difficult if you had to write these systems in these hacky ways. People may recall doing work early on, before some of these frameworks. It was very, very painful to do neural network research, right? Did anyone take Andrew Ng's MOOC way back in the day? And yeah, I've seen a bunch of nodding. Yeah, the MATLAB-based neural networks. There's only so ambitious you're only gonna be so ambitious if you're using MATLAB as your framework, right? And so part of the idea is, OK, can we start to do some work on developing what would kind of a torch look like for this network of networks era, where you're composing calls across different models, et cetera. Yeah, and the goal is, you want things to be, really, really simple and quick to express a new idea, and you want that idea to run efficiently and quickly as well. The pain of every researcher's life is waiting for experiments, and when you start to, ensemble these LLM calls, it can be super duper slow, and so these experiments can take a while. So you want to parallelize things. You want to dispatch things all at once, especially if you're calling open source models on top of frameworks from our lab like VLLM or SGLang. You need to make sure you're getting really, really high utilization of a GPU, able to make as many calls as you can with as few resources as possible. But even for calls to these API providers, you want to kind of saturate the API, spam as many requests at them as you can until they turn you off for DDoS. That's the goal, right? I'm trying my best, right? And so, I'll give a couple of code snippets to give people intuition for how you build these systems. You might have seen this earlier today, but a lot of information is being thrown at you, so repetition is not the worst thing. OK, so there are really three syntaxes that people have built. One is just regular functions, but then there are these kind of two syntaxes that researchers have been using. This one actually I kind of like. It's this little string-based syntax that's just an extension on top of the base framework that I'll show you on the next slide. I like it because it's just like a couple of lines, and it's really intuitive to figure out like what's happening with like a, just reading a single line. So here, this is just a really basic graph defined by this just basic list with a couple of components. So the first component is an ensemble of 101 members of just GPT-4 calls, all GPT-4 in this case, with temperature of 0.7. And then the next is a judge with Claude 3.5 Sonnet and 0 temperature. And then that system becomes a graph, and then you can kind of call that like you would any other function, giving it queries, and it will kind of answer the question by passing it through this graph in a unique way. One other kind of funny point is you can have kind of cross-provider graphs as well, where you can have subgraphs. And this is also 101 models, but across providers. So you've got GPT-4o, Claude 3.5 Sonnet, Gemini 2.0 Flash, Claude 3 Opus as a judge. And you can kind of dispatch the request across different providers. Also, I'll note the GPT-4o call on the back end can also be dispatched across providers of that same model. So you can call both OpenAI first party, and if you have API keys, you can call Azure OpenAI across regions too. So you can get kind of a lot higher throughput. So instead of 10,000 requests per minute, you can have 60,000, 70,000, et cetera, at the same cost. Actually, that's an important point. One of the things about the cloud that got people at Berkeley actually really excited back in the day, if anyone read Above the Clouds of Berkeley View on Cloud Computing, was the idea that kind of fast is free in the cloud. That was like the revolutionary thing. Right? The idea that if you have some job that would run for a day on 10 machines, in the cloud you could run it for 15 minutes on 1,000 machines, and it would cost the exact same, as long as it was kind of horizontally scalable. You can go 100x faster for the same cost. That was like a revolutionary thing. Obviously, that got people really excited about things like Spark, right? As you can kind of parallelize these Spark requests, and that set off this big wave, people trying to move things to the cloud, so you could take advantage of this, right? And that's a really important point, and you want to be able to do similar things with these inference calls. Here's a more explicit way of defining it. This is kind of more like PyTorch. You've got some typed input, typed output if you want. So you can specify this is what an input has to be, and you can also put more logic in here and have it meet some desiderata. You can obviously output as well, but the simple part is you can define this module, which is an operator. In this case, it's just an ensemble and judge system with a parameterizable width for the ensemble. You inject that at runtime, and you define this eagerly, right? So the forward method is written just like PyTorch eagerly, where you're just kind of doing operations in a Pythonic way. But underneath, it's kind of like TensorFlow, like Jackson XLA, in the sense that there's an IR being constructed, kind of an intermediate representation of the graph, of the DAG and the dependencies is being constructed. And that IR can be grabbed and ported. It can be moved client side and run, if you want to. It can be run server side in some intelligent way. You can lower it. You can re-optimize it. You can do interesting things with it. And that's what the JIT is doing. So kind of like JAX in some sense. You just JIT the class, these operators are all pi trees, so it flattens it to a pi tree. And then you can do things like topo sort. Like the things that basically undergird things like Megatron, undergird all these frameworks for running transformers. Otherwise transformer inference would be painfully, painfully slow. Similar concept. And then once you have that thing defined, you can call it like any other Python function on prompts. In this case, by the way, these operators, these are kind of from the default non-library. So kind of like nn.linear, nn.dropout, and PyTorch. You have like non.uniform ensemble, non.judge synthesis. So there are kind of base prompts that you can kind of go in and tweak. Or you can just kind of take the base prompts as you would and like not worry about that detail. Yeah, there's some other things that people use a lot. So for example, just like how JAX has VMAP functionality, so you can have a graph and a set of inputs, a batch of inputs, and you can efficiently run that batch of inputs and that graph, right? And so you want to kind of parallelize across both the graphs components and the inputs and get high utilization out of that. So it has utilities like that. It also, both in the string format and obviously in the operator format, you can also define reusable subcomponents that you can kind of name. And then those subcomponents can then become branches, kind of elements in a larger graph. So you can have a tree that is itself a leaf in a tree, right? So these kind of nested compositional structures, just like with transformers, right? Yeah, there's also this models library. I won't go too much into it, but yeah, basically you can grab an instance of a model without dealing with the peculiarities. This is actually something that the group built independent. There are some great frameworks for this now, like LightLLM, if people are familiar with that. But this is basically kind of like LightLLM. It's just if you want to use GPT-4, Claude, some local model, you can use the same API for all of them rather than dealing with the quirks of their respective frameworks where they have these funny syntaxes, .chat completions, blah, 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 blah. Right, these weird message formats. They have different names for the same variable. Some are like temperature, some are temp, etc. And then you blow your brains out. It's pretty bad. And then also some really simple utilities for data sets. GPQA, Amy, all these data sets people always use. Parsing them from Hugging Face or wherever. These things can just be really tedious if you're trying to do research. This isn't the fun stuff. This is the drudge. And so just some shared utilities for all of that. Yeah, and as a last point, one kind of really cool thing about the system is one of the painful things about some of these frameworks is they're too opinionated sometimes. You have to write all of your logic in the language of that framework. You have to use these utilities and kind of add nodes. Well, one nice thing about the Simba framework is you can take kind of arbitrary functions, and they can be, if you wrap them with this decorator, they can be turned into operators underneath, giving a lot of great functionality around error handling, the IR capabilities, some of the execution, intelligent execution, just from like writing arbitrary functions. And you can also use arbitrary functions inside of operators and vice versa, and it handles that pretty gracefully. So you don't have to use that kind of operator class if you don't want to. You can just write normal functions, and it will, construct a class if you just wrap. Yeah, so that's basically it for sharing that. You get the idea. A lot of interesting work going on. I'll highlight a few things that different people are doing. So at least that I've been told I can highlight. There's a lot of interesting work on using these compound systems to generate novel data, kind of almost within the RL loop, generating reasoning traces, generating synthetic data. Alan and Parth have been doing some of that. Omar has been doing a lot of work on optimizing prompts for these compound systems, which is actually really interesting. It's almost like these compound systems are like agentic companies or agentic organizations. And so, one common paradigm is you can have agentic manager, agentic workers. And the question is like, okay, what should the prompt from the agentic manager to the workers be for the workers to be most efficient? And should you have different prompts for different workers? Like, it kind of gets really fun. And DSPy, which Omar built, optimizes that for kind of single model calls, but then extending that idea to these systems of model calls increases dimensionality a lot and gets really, really interesting. Yeah, a lot of interesting work on, on kind of, I'd say methodological work on using these compound systems for understanding uncertainty from these models better. These models aren't yet perfect at having a calibrated sense of their uncertainty, and so that's what we talked about earlier with building ensembles. You can get a sense for how much the ensemble members disagree. The kind of entropy across answers is a really good signal for whether you're going to get a good answer or whether it's going to be gibberish, and it's kind of hallucinated just to make you happy. So there's work on that. There's work on, and there's a lot of applied work. There's work on running these things in batch mode more efficiently that Deepak and NVIDIA has been doing. There's work on science. So a lot of interesting work across a number of areas. All right, so that's basically it. Yeah, feel free to reach out to me, by the way, if anyone's working on cool stuff. I or others in the community would love to chat about what you're dealing with, what type of agentic systems you're trying to build. If you have ideas for how to make these general methods better, that's also awesome. So yeah, ping me, and we'd love to chat. And I'll be a router node, but there are other people in the group, in this group, that if you want to talk to them, let me know, and I can loop them in or route to them. And there's a lot of other people that are on here as well. They're doing really awesome stuff that, and connections to be made. Whatever problem you're dealing with, probably someone else is dealing with it too, and they may have figured it out. There's many cases like that. And that's one of the most fun things to do is like connect someone with someone else who figured out the problem they're trying to work through. That's really rewarding. Okay, I'll make this controversial point again because I like to make it, and it's like a PSA. I really want us to stop calling these things agents, without at least referencing this kind of original definition of agents, right? So this is a good time to mention this. The winners of the most recent Turing Award were Sutton and Bartow, and they won it for their contributions to RL, right? Turing reinforcement learning. And this is where, at least in the AI context, the initial kind of definition of an agent really came to the fore. And the agent was defined in terms of this framework, this kind of classic framework, where an agent is defined by its ability to take actions. It's defined in context of an agent in an environment, number one. And the agent is defined in terms of its ability to take actions on the environment. And the environment produces rewards based on the action of the agent that then go back to the agent. It's kind of defined, so you can't really have an agent without having the agent ability to take actions on some environment, right? And there's some notion of rewards back from the environment to the agent. In this framework, there's no notion of memory. There's no notion of tool use per se. That could be one of the actions, but not necessarily. Some of these desiderata of a useful agent aren't part of the definition of an agent. They're things that we want to build really powerful agents. Just like how a neural network isn't defined by having external memory, like a neural Turing machine, that's a specific construct, right? The neural Turing machine. Yeah, similarly with these agents, under this definition, I think the original work that was done by Adept, was actually some of the original work on agents, where they had these large action models that just took in observations from pixels and then produced actions, and would build spreadsheets and such back in 2021. This was probably ahead of its time in a lot of ways. And now, obviously, we have these much more rich agentic systems. Work like Gorilla has been done to make these agents good at using tools. There's work like MemGPT that's made them good at using external memory. There's a lot of work on kind of making agents good. But I think that's these are kind of things that we want from good agents. These are desiderata. These aren't part of the definition of an agent. And so I want to separate the idea of compound systems from the idea of agents. They're related but orthogonal. Obviously, you want an agent to be reliable. And to make an agent reliable, these things around reducing hallucination, understanding uncertainty, they're all useful properties, but they're not part of the definition. So please help me in evangelizing this. It's so painful to have every academic conversation is is that an agent or is that a workflow? I'm like, oh, please stop, make it stop. So you get the idea. Okay, cool. So I'll pause there. Maybe we can do some questions, and then I'll pop open a GitHub and just walk you guys through some aspects of a repo with some of the remaining time we have. And yeah, people can all clone the repo and follow it, and then contribute to it. There'll be some good stuff being added there over the coming 2 weeks. I think the 15th of August. Yes, I don't have my watch, but yes, 15th of August. Good. Okay, so let's pause there and maybe some questions and discussion.
When you build networks are
Yeah.
more complex topologies.
Yeah.
So one thing I see you mention is it leads to the possibility of comparing outputs.
Yeah.
But have you measured and found that concrete improvement because of that?
Yes. Okay, so the question was,
No, sorry.
Yeah.
I remember what Andrew ever talked where he did show.
Yes, great question. Yeah, so the question was, part of this compound systems or network of networks concept, in it there's an obvious notion of you can compare answers. And so the question is how have you looked at measuring, comparing across answers from different models? Is that faithful representation? Okay, close enough. Yeah, so I think we've done a lot of work on this. There's a work, I was going to pull it up, but people can search it, called LLM Selector that collaborator Ling Zhao led. And it was basically looking at you have an agentic task that is defined as agentic because you're taking actions and there's multiple steps. So it's a multi-stage pipeline, quote unquote. And so instead of it being a single call, one shot, you have like 3 different steps that define some task. So it's like you first have to pull this information from somewhere, then you have to find something in the information, then you have to use that to then open some, log in somewhere, et cetera, et cetera. So it's kind of a long horizon setting. And the basic question asked there was, okay, are different models from different providers better or worse at different subtasks or at different tasks? To a very dramatic degree, and to what extent can you, by optimizing across providers, do better on an end-to-end task than if you had a single provider? And basically the result was the mixed provider system that intelligently selected the best model to do a subtask was far more effective, between at the lowest end, like 15 in the most recent variant, % better on these kind of really hard agentic benchmarks. On the high end, like 243% more effective at a lot of these tasks in terms of success rate. So dramatically more effective. And they were never worse. It was like monotonically better. Always better. And same cost or lower cost, actually, as well. Versus that kind of 15 to 243%, that's versus the best single model. So you have like 10 other models. You take the best end-to-end performance of those, and then this mixed system was doing better than the best of those. So it actually kind of shows that by combining models across providers, you can do stuff that the providers can't do themselves, which is very intuitive. But I don't think something that we appreciate broadly enough yet. And so yeah, these models are good at different things. And there's a lot of work starting to show that. I think the work from Jan Stoica and some of the LLM Arena people is really good to follow on this. They've done a ton of work on eval broadly and on LLM as a judge, and on the biases and affinities of different models. And yeah, these models are different, or better. They're different. They're better at various things, worse at various things. And that's getting more and more extreme as RL is becoming more the primary regime by which we're making these things better. In the pre-training context, we're all using the same data, right? It's kind of, there wasn't that much difference in the recipe. With these RL systems, there's a big difference, like the data mix, the shape of the RL function and the objective. Like these things are very different, and these systems diverge more. So these models are getting more and more different from each other. You actually have to make kind of almost product decisions about what you want the model to be good at and bad at in a way that wasn't really true in the pre-training era when everything was just general. So now it's getting more and more deliberate, and these models will, I think, get more and more different over time. Yeah? Yeah. You have a question? Oh, no. Okay, cool. Yeah.
You're asking the difference in possible models, and then you're comparing like the different answers, the responses that they give. And I think there was a part you mentioned how like the cost of doing this has decreased over time.
Yeah.
And I wasn't quite sure how that would decrease because intuitively it's like if you're making several calls, that's very expensive.
Yeah. Great question. So. Yeah, I'll repeat the question. Yeah, the question was about kind of some of the economic implications of all of this, and how if you're making calls to multiple models, how we can say that, hey, the cost is, this is an economically efficient thing to do, and how is the cost of this? How can the cost of this be cheaper? I think the best example to illustrate this would just be this. So this is a side-by-side comparison of O1 Pro, the O1 Pro spec sheet from OpenAI, and the R1 spec sheet from DeepSeek. So R1 is a pretty good model at various things, and the price per million tokens, depending on cache hit, which is kind of a funky thing, is only 3 cents. The price per million tokens, this is input tokens, the price per million tokens of O1 Pro, $150. Right? That's a big dispersion. That's 5,000x dispersion. You can make a lot of, you can make a lot of these R1 calls for the price of a single O1 Pro call. And that, by the way, is per token. These models are also different. They're verbose to different degrees. Right? And so there's a lot of just these differences among models. So long story short, if you use these models well, if you compose calls to these weaker models in an intelligent way, like a verifier-prover structure on R1, even if that is 5 calls, you'd still be 1/1000th the cost of O1 Pro. And so one of the best examples of work illustrating that is actually work by Alex Demakis here at Berkeley, who was a faculty in Skylab and EECS. And Alex basically created this super simple regime that he calls laconic decoding, where he'd basically take 5 R1 calls. Academics like R1 because it's open source, right? He'd take 5 R1 calls, and he would basically notice this quirk of R1, where, long story short, when it's stuck, it's very, very hard working. So it'll keep trying. More thinking time is basically more effort. And it's kind of like searching. It's like a tree search over like different approach paths. And if it gets stuck, it'll backtrack. And so basically what he found was that the longer the thinking traces were, the more likely it is to get the answer wrong because it went down a wrong path initially and wasn't able to backtrack before it ran out of time. And so roughly speaking, he found that if you ask the same question to 5 replicas of R1, and you pick the shortest answer, that shortest answer had a much higher probability of being correct than the longer answers. Just an interesting quirk of that model. And so using that quirk, he said, okay, I'll just create a simple algorithm of early stopping and selecting the shortest answer. So basically you run 5 replicas, DeepSeek wraps its thinking in these kind of thinking tokens. So you wait for the first thinking token, then you stop all the replicas and return that answer. They got the thinking token. And that simple protocol is faster, on average, than a single replica. It is smarter on average than a single replica, but ironically can actually be cheaper on average than a single replica. Wait, how is that? You're creating 5 replicas. How would that be? Well, it turns out when the model gets stuck, it might generate a ton of tokens. And output tokens are more expensive than input tokens, by the way. It might keep going, and you're paying per token. So if you stop the ones that are going down the wrong path, you can actually, in expectation, even over 5 replicas, save money. And that's like a super simple example of creating 5 clones and kind of grabbing the fastest one. But that kind of gives you some intuition for, oh wow, like if even that simple thing helps, what types of more rich things could we do? What other gems lie in this architectural space? Right? That gives you some intuition. Great question. Yeah. Any other questions? Yeah.
Yeah, I was just going to kind of expand on what we were just talking about, which is,
Yeah.
is there good research on how to synthesize something out of the output of a bunch of these that is greater than any single model's output, and like what does that look like?
Yeah. There's a few works. I referenced some of these. Maybe, yeah, I'll go on this slide. Yeah, I referenced some of them. Maybe I'll note some of these. Yeah. 2 of them that I'll note is one is this ensemble space work. It's actually a really simple idea, but there's some richness to actually being able to use it. But long story short, simple idea. It turns out that if you build kind of a group of these models, a committee of models, that committee is very good at getting a better answer to easy questions. So it's kind of funny. If it's a question where the base model by itself would most of the time get the answer right, but every once in a while it might hallucinate, putting a committee is kind of a variance reduction mechanism. It'll kind of squash the probability of hallucination. Right? Ironically, though, so that means it helps a lot for easy questions. And you kind of see this monotonic improvement on easy questions. Ironically, though, for hard questions, questions where a model by itself would get the answer wrong, doing consensus in committee makes the probability that you'd kind of get that spark of insight to get the answer right very, very unlikely.
Yeah, it's like regression to the mean, where the mean is useful in simple questions and bad in complex.
Exactly right. Yeah, variance reduction, regression to the mean. And so in those cases, having more calls, which by the way, intuitively, that's when you probably would have even wanted to use this type of approach. Like you'd probably want to use the approach of making multiple calls for hard questions, intuitively. Turns out it makes everything worse. So not only did you spend 100x, 1,000x more money, but your answer is actually worse. And so that you're pretty unhappy in that case. And so you kind of need to be able to discriminate between easy and hard questions to apply the scheme appropriately. Right? And so that's kind of one small example of some of the types of things that have been done. But yeah, it helps. If you're able to do that well, then you can kind of use this idea to almost route. But instead of routing amongst models, you're routing against these kind of architectures.
Yeah, it's like a different kind of semantic routing.
It's a different type of semantic routing. Same thing with the best of n graphs. The best of n graphs actually turns out is a really simple primitive. It's almost never worse. In none of our experiments was it worse. It's kind of like O1, where you might have seen, if you recall from the early O1 model card, O1 was not better at some things. Like if it was creative writing, they said it wasn't helpful. But it was helpful on math and code. Same with some of these architectures. Like they're better at some things, but they're never really worse. And so that's something that just in general, I think if there's like one thing that people should try, it's if you have a sticky task, the simplest thing you should try first is just creating a little graph with 5 models. Same model, different models, doesn't really matter. 5 of the models that you think would be good. Having those all generate their own base answers, just giving them the question, having them generate answers. And then having a simple judge, where the judge prompt is basically, here's 5 different perspectives from your advisors. Considering this perspective in the original question, answer the question. In the most simple case, just like a synthesis judge. You can also just select or whatever, but just the most simple case is just that. Just like give all the answers to a judge and tell it to give you a final answer.
So it actually synthesizes across the answers.
It can do that too. Yeah, it can do that too. Yeah. That simple thing will probably help in a lot of your contexts. Yeah.
Is there a suitable number of how many instances are optimal for?
Yeah, the question is there a number of how many instances are optimal? No, partly because of the dynamics I just mentioned, where there's more richness to this than you'd think. It depends on your question, depends on whether it's easy or hard, depends on a number of things. I'd say probably as like a simple thing, I recommend just like something reasonable like 5. It's just to almost just kind of be really prescriptive. I think 5 calls, just try that. And if that helps a little bit, then you can try to push it further, right? All these things, like the reason this is so rich is it's a function of your specific setting and your SLOs and SLAs, right? So for example, if you have a task where, like, I'll give Harvey as an example. Harvey's a legal AI company. The briefs that they generate with LLMs are really, really valuable. They're not that many words, but like people pay a lot of money for these reports. And a good report is worth a lot of money. 1 million tokens sounds like a lot, but 1 million tokens is like 5 books. It's a lot. Like $150 per million tokens is actually not that expensive if you think of it that way. And so if I only want 1,000 tokens in like a report, I'm willing to pay $1,000 for a good report. I want to give you more money. It's like, please, OpenAI, take my money. Like, I'll pay you more for a better answer. Is how, if better, yeah, exactly. So that's kind of how people think about this, right? And so what I think part of what we're trying to do as a research community overall is find methods that can better assimilate money, or compute rather, and turn it into good answers, right? Kind of have some scaling curve like that. That's exciting when you find those, right? And, so depending on your problem, you might find that 1 call is enough, 3 calls is enough, but maybe you keep getting improvement in your task as you add calls. So it depends on your setting. Yeah. Yeah, please.
On the same topic, but this kind of reminds me of the secretary problem. Right?
Yeah.
And so it's like, many people do some sort of cook until done thing where it's like,
Yeah.
just going to do X of these, give the judge that context,
Yeah.
this has happened, and then find the next good answer that comes out of it.
Yeah.
Is that relatively successful in a broad range of questions?
Relatively successful in a broader range of questions. In fact, actually, the network of networks paper that is kind of mentioned here implicitly in that best of n graph context, and I showed it on a prior slide, that paper looked at these judge-based systems and kind of a cryptographic way of analyzing them. Long story short, as long as you have a judge that has, I would say, is more likely to certify a correct answer than it is to certify a wrong answer. That's it. It's picky. It's not perfect. As long as it has a better than random chance likelihood of saying a correct answer is correct versus a wrong answer is correct. That is the only criterion necessary to be able to kind of put, to get improvement as you increase K, aka the number of ensemble members. So it's pretty simple. That's really it.
That's fantastic, honestly.
That's really the only principle. If that principle is just satisfied, then you can put more and more compute into this type of.
Then you can go back to the here's more money, you get a better answer.
Here's more money, you get a better answer. Now, the rate at which you get a better answer might not be satisfactory. But you want to push that. All right. Exactly. At some point, your boss, is going to come in and say, does this make sense? But yeah, I think the takeaway thing. So if people want to follow this line of work, feel free, as I said, to reach out to me. If you're doing work on things and want to, talk about it, love to talk about it. Here's my personal email. Also, you can follow pyember/ember on GitHub. We're going to be pushing some great updates. We already have some great code there, but we'll push some new kind of improved version of that framework, along with a lot of research from different collaborators in the coming couple weeks. Yeah, so look forward to talking more. Thanks for your attention.